Welcome to another exciting adventure of Tip or Slip, in which case we propose a much harder problem. Here's a turntable, here's a spindle in the middle of the turntable, and here's the thing that you have to worry about. I've placed a box on the turntable. Ha 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 ha. Now, I was thinking about this on my bike ride and I thought, wow, what a cool problem. If it's rotating, then we know some things. We know that the net force in the y direction is 0, right? And that gives us that the normal force minus mg equals 0. Probably the normal force is going to have shifted over to this side. So here's Fn, and here's mg down right there. Oh gosh, that's kind of messy. Let's make it a little bit bigger. I'm knowing some things like mg down and normal force up. And those are going to be the same magnitude here. And what else? Well, let's just organize that. Fn is the same thing as mg. And then I also know that there's going to be a static force of friction. And the static force of friction could be up to some value. So let's say that the static force of friction is at the very maximum, what I'll call Fs max. But Fs max is just mu times Fn, which is mu times mg. All right, cool, that's fine. Also, Fs, interestingly enough, if we're saying that Fs is the force this direction, then we know there's acceleration, right? And Fs is providing that acceleration. Fs equals, well, it's gonna be v squared over r, that's the acceleration, but it's gotta be multiplied by mass, because that's the only unbalanced force, because those two are the same force. All right, and that's fine. Well, let's go into it. Like, what if we solve this? What do we get? We'll get m times v squared over r is greater than, I'm going to say if, mv squared over r is greater than mu sub s times mg, then we'll get slipping. What that says is the required centripetal force to keep it going in a circle is greater than the static force of friction can provide, in which case we would get slipping. So we're going to have to come back to that, but I'm just going to say if mu sub s, I'm going to have to change colors here because it's getting kind of nasty. If mu sub s is less than v squared over gr, then we'll have slippage. And I could also substitute in an omega, that might be fun as well. If mu sub s is less than omega squared r over baby g. Okay, cool. But here's the problem. Oh gosh, well, let's go a step further. We could even solve it for velocity. We could say velocity is greater than mu times g times r, screwed, right? I pronounce this the screwed of Muger, which is really fun to say. Try, build a video game around the screwed of Muger. And then omega would have to be greater than, what do we need now? Then we need mu sub s, this is mu sub s here also, mu sub s times baby g divided by the radius. Now, of course, that's the radius from there to there. That's the radius of the circle that the thing is experiencing. And I'm going to have to define things like w and capital H, the width and height of the thing. I'm not going to use r. I'm not going to pretend this is a cylinder for the thing on the turntable, because I want to leave r as the distance between the center of the axis of rotation for the whole turntable. All right, now, does this feel comfortable? This to me says, see, this is always weird. I like putting these two next to each other. One of them says that the speed has to get, well, these are slip, right? If I have a bigger radius, then the speed would have to be bigger for it to flip. And this one says if I have a bigger radius, then the omega would have to be smaller for it to flip. I think this is the more intuitive equation, because it says if I'm on I'm standing here on a turntable or a merry-go-round, if you will, and in terms of me slipping, that slipping is going to happen much more easily if I'm farther out. So that is provided for by having a larger radius, and so if I get farther and farther out, then my speed needs to increase, but this equation says I just need to rotate the dang turntable a little bit faster. Now, that makes sense, but I have a big confession to make at this point. You're in an accelerated reference frame. When I drew this picture, pretending I had equilibrium for this poor box that I set on a turntable, my mind camera was zooming around on the turntable and always focused on that box. So in order to stay with that box, my camera in my mind has to be accelerating. That's a big problem. The acceleration of this center of mass means that Newton's laws are no longer valid. Everything that I've been teaching you has to be thrown out, and this might cause you to panic. You see, I'm not allowing it to accelerate when I draw a picture of it right here. I'm trapping it in one location, but the only way I can actually treat it as if it is accelerating, or rather acknowledging that it is accelerating, is I can introduce an ugly, disgusting computational tool, and that is a fictitious force. Some people call it an inertial force, a force that represents the effects of inertia, which should never be drawn on a free body diagram. But this force is representing the effects of inertia in an accelerated reference frame because I don't have any other way to include the fact that it's an accelerated reference frame without doing some pretty heavy math. So I'm going to do that by including a force that acts outward, and this is going to make me feel very uncomfortable. I want you to work with me here because I'm going to draw a force outward, and that force outward is going to be called the centrifugal force. This is centrifugal force, and it's sort of equal to the centripetal force inward. In fact, I'm going to argue that now that I have a fictitious accelerated reference frame sketched right here, I have a box that's in, quote, equilibrium, unquote. These two forces are opposing each other. This one's just not real. Ha, 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 ha. The reason the force acts outward, even though the actual net force is inward for an accelerated reference frame, is just like when you look at the globe. You stand on the globe and you see the sky. Have you ever looked up at the sky in the evening time? Look up at it for a few moments. You will find that the sky appears to rotate clockwise. This is the sky going around above you. And raise your hand. I can see you. Raise your hand if you think that the sky is actually rotating clockwise around the entire Earth. That is a cute perspective. I think it's fallen out of favor lately. Let's say that the firmament is fixed and the Earth itself is actually rotating counterclockwise. That would explain the same vision. So it's a matter of perspective. It's a matter of perspective because I know that the net force is actually to the left, but if I'm on the rotating thing, I feel like that centripetal force is to the right. It's just an internalization of the experience. So now I have a completely different free body diagram. Okay, it's just slightly different. Let me draw it kind of carefully. This paper's all lined up right here. Here is the free body diagram. Battery's dying. Gonna come back to the free body diagram in a moment. Meanwhile, the accelerated reference frame. I still have an axis of rotation that's right here. I've got a dot in the middle. mg is still acting at the center of mass. The centripetal force now acts at the center of mass. It's a centrifugal force. And it is m times v squared over r. Same form, just the opposite direction of your actual understanding of the system. And then the normal force is as big as mg and it acts straight up, and the force of static friction acts this direction. So I suppose all of these things, this accelerated reference frame, this is really useful for us to consider whether it will tip. We've already figured out whether it will slip, and now we need to look at whether it will tip. Oh, by the way, we didn't need to concern ourselves with this regarding the slipping because that was in those forces were in the horizontal direction, and didn't matter whether we had a rotating accelerating reference frame or not. Okay, so regarding the tip, what else do I know? It seems like I know that this is also equal to mu sub s times mg. Because it's f sub s, we're going to assume that we've got just enough force to keep this in equilibrium, and the net force, that means the net force in the x direction equals 0. It's the sort of net force in the x direction because there is actually acceleration, but we're masking the acceleration right there. And including rotating frame effects. So this guy is now not accelerating in the accelerated reference frame. That's what I mean when I say there is no net force, because it's in the accelerated reference frame, which is accelerating, but within the frame, it's not accelerating. Okay, so I'm gonna define tip to be, now I need to just take this, no space, poor setup. Orange, orange. So we'll tip when the torque from the centrifugal force is greater than the torque from mg. Would you agree that those are the only two guys who are going to be making any torque around that axis of rotation? This is actually a very simple problem then. The torque from the centripetal force is mv square over r times h over 2. Let's see if we can get h over 2. H is the capital height of the whole thing, so that's this distance here. And the r perp for the centripetal force is in fact half of h. It's that distance right there. So I need that to be greater than mg, which is the force. Now, where does mg act? Well, it acts at w over 2, because w is that distance right there. mgw divided by 2. Looking at that, I happily see that the 2's cancel and the masses cancel. There we go, masses cancel and 2's cancel. So I've got this relationship for tipping. This will cause a tip if that is true. The centripetal force will cause a tip that direction. Otherwise, the normal force is just going to shift back a little bit this direction and prevent mg from knocking the block through the turntable the wrong direction. Like, completely unintuitively, would you expect this to plop into the turntable? Well, I wouldn't. Fine. So I'm going to solve this for v, and it says if, we have to do if in a bold black color. So if v is greater than or equal to, because I'm going to allow just barely tipping, right? I'm solving this for v, so I get g times w times r, gwr, divided by h, screwed. I'm talking about that. If v is greater than that, then I have a tip situation. Okay, but we had this other statement that said if, I'll bring it back over here for you, but if v is greater than mu sub s times g times r, then we have a slip. So these two situations are different and interesting. So I kind of want to look at whether one will be possible or the other will be possible. So I'm thinking I should compare these two guys. And I'm going to assume that the V has gotten sufficiently big. Like, if it's not tipping or slipping, then who the heck cares? So let's put these two together and compare them. I'm going to argue that if this is the bigger term, then it will never slip. Now, does that make sense? Sorry. Then it will never tip. If this is a bigger term, then V can't be bigger than this and not also bigger than this. As V gradually increases, as I spin the turntable faster and faster, this will happen before this ever happens. So it's only slipping if this term is bigger. Conversely, if this term is bigger, then it will only tip. So I'm going to write that mathematically on the next page. And that page will look like, let's see, I'll put this here. If, oh, that's a nice bold color too. If GWR over capital H is greater than, here's this other term, mu sub S times G times R, both of these are underneath scroots, then what did we say? If this one is bigger, then this condition will never be met without this condition also being met. Then slip. Then slip. And the converse is also true, but we'll clean it up before writing the converse because I see some things that cancel. I got some G's canceling. I got some scroots canceling. I can do both two things to both sides of the, algebra says I can do the same thing to both sides of the equation, great. So, the condition then is if, and I have to switch colors again, if WR over H is greater than, oh shoot, the R's canceled too. Why didn't you tell me? Look, the radius doesn't matter either. Now, of course, the radius matters for when it will slip or tip, but whether it will slip or tip doesn't matter where you put it. It will either slip or tip based on elements of its geometry and based on that mu right there. So here's what I've got. If W over H is greater than, oh, look how simple it is. Don't you love physics? I love physics. This is so simple. If, then slip. Is so simple. But if, if mu sub s is greater than W over H, then it tips. This makes so much sense because it says that if mu sub s is sufficient, then it will tip. Okay, let's make a graph. This will be really fun. I'm gonna solve this equation for W. If W is greater than, not an equation, an inequality. If W is greater than mu sub s times H, then we have tipping. So now I'm gonna make you a pretty graph. Watch this. Axes are the width of the thing and the height of the thing. This is a box that I've set on a turntable, and we are learning something today. I'm going to draw you a line, and I'm going to tell you that its slope equals mu sub s. So I don't care, maybe it's 1, maybe it's a half, I don't care, but everywhere up here, W is greater than that stuff right there, and I said if W was greater than that stuff, wait a second, I just got myself confused. Oh shoot, I switched this around. This should say W is less than, there we go, whew, good. If W is less than mu sub s times H, then we've got tipping. So I'm gonna put a tip label down here, and I'm gonna say everywhere down below this line, it will tip. That makes sense because the height's so big and the width is so small. You're talking about one of these suckers. Of course that will tip if I put a pencil on its eraser and spin it around on a turntable. But what about if the width is bigger than the height relative to this mu sub s thing right here? Everywhere over here, we've got slipping. And everywhere over here, we've got tipping. And we've described all of geometry space then, the relationship between the width and the height. So I guess if the width is equal to the height, then it will slip, assuming that mu sub s isn't 1. If mu sub s were 1 or greater than 1, then it could possibly tip. But in most circumstances, you're gonna have a mu sub s slightly less than 1 or way less than 1, in which case it will slip. Slippery things slip, go figure. Sticky things might tip. And they put that rubber stuff on the back of some of those fancy mugs, right? Rubber stuff on the back of those fancy mugs. Those are gonna tip over. See ya. Slipping! Times mg, then we'll get slipping. What that says is the required centripetal force to keep it going in a circle is greater than the static force of friction can provide, in which case we would get slipping. So we're gonna have to come back to that, but I'm just gonna say if mu sub s, I'm gonna have to change colors here because it's getting kind of nasty. If mu sub s is less than v square over gr, then we'll have slippage. And I could also substitute in an omega, that might be fun as well. If mu sub s is less than omega square r, right? Cool, that's fine. Also, fs, interestingly enough, if we're saying that fs is the force this direction, then we know there's acceleration, right? And fs is providing that acceleration. Fs equals, well, it's gonna be v square over r, that's the acceleration, but it's gotta be multiplied by mass, because that's the only unbalanced force, because those two are the same force. All right, and that's fine, Well, let's go into it. Like, what if we solve this? What do we get? We get m times v square over r is greater than, I'm going to say if, mv square over r is greater than mu sub s. Probably the normal force is going to have shifted over to this side. So here's Fn, and here's mg down right there. Oh gosh, that's kind of messy. Let's make it a little bit bigger. I'm knowing some things like mg down and normal force up, and those are going to be the same magnitude here. And what else? Well, let's just organize that. Fn is the same thing as mg. And then I also know that there's going to be a static force of friction. And the static force of friction could be up to some value. So let's say that the static force of friction is at the very maximum, what I'll call Fs max. But Fs max is just mu times Fn, which is mu times mg over baby g. Okay, cool. But here's the problem. Oh gosh, well, let's go a step further. We could even solve it for velocity. We could say velocity is greater than mu times g times r, scrooted, right? I pronounce this the scroot of Muger, which is really fun to say. Try, build a video game around the scroot of Muger. And then omega would have to be greater than, what do we need now? Then we need mu sub s, this is mu sub s here also, mu sub s times baby g divided by the radius. Now, of course, that's the radius from there. Welcome to another exciting adventure of tip or slip, in which case we propose a much harder problem. Here's a turntable, here's a spindle in the middle of the turntable, and here's the thing that you have to worry about. I've placed a box on the turntable. Ha 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 ha. Now, I was thinking about this on my bike ride and I thought, wow, what a cool problem. If it's rotating, then we know some things. We know that the net force in the y direction is 0, right? And that gives us that the normal force minus mg equals 0.